Section 2.3.5, modeling critically damped motion. We've done underdamped motion, we've done overdamped motion. We're left with one specific case, that's critically damped motion. It is mathematically an overdamped case because it doesn't oscillate, but it is the limit of the overdamped case as we add damping. And because it's at the limit, we can get a slightly different solution for our quadratic expression. Again, this is when zeta is equal to 1. Lambda will be equal negative real numbers, which is a little bit confusing because we get lambda of 1 comma 2 is equal to negative zeta omega n plus or minus omega n square root of zeta squared minus 1. So what that means is you get lambda 1 equals lambda 2, which is just equal to negative omega n. All right. This is where you kind of have to trust me a little bit. This is an applied mathematics vibrations course. Math can give you a lot of solutions that might not be useful all the time. And what we're going to do is use some mathematical tools to get us to a solution that is useful, right? There's a lot of different ways that you could rearrange these variables to get there. This is just one way that we're going to do that. Because both solutions, A1 and A2, are the same, we can multiply the second one by T so that the solution for a critically damped system is in the same form as below. That gives us an equation of motion of x of t is equal to A1 e to the negative omega n t. That's what we had before, right? That would be following the same solution we had before. Plus A2, I'm going to multiply it by t. I didn't take the derivative. I'm just multiplying it by t because I choose to multiply it by t. E to the negative omega nt. Again, we are looking for a solution for equation of motion, right? And one of the ways that we can get a solution for an ordinary differential equation is just to guess and check, right? So that's the thought process that we're working down now too. This becomes x of t is equal to A1 plus A2t, just pulling those out, e to the negative omega nt. So I can see that I'm going to get a decaying shape, and I'm not going to get any oscillations. And so that equation represents a non-oscillating response of the equation of motion. And so again, we have to solve for A1 and A2 using the boundary conditions, x naught setting t equals to 0, getting x dot variation of this equation of motion, setting t equals to 0. And that will give you A1 is equal to x naught, and A2 is equal to v naught plus omega n x naught. And this is your solution to a critically damped system. And then the question is, how do you know that's correct? You can build an experiment and test it, right? This is an applied mathematics course. The applied part means we're also going to rely on some mathematics to get us the solutions that we need. We end up with a lot of solutions that we throw away as we go. It's not a pure mathematics course, and it's not a pure experimental course, right? It's applied mathematics.